Rigid body equilibrium. A rigid body is a collection of connected particles. For example, we can view a bar as being a collection of an infinite number of particles arranged in a specific manner, like this. The concept of static equilibrium, as was explained in ST02, also applies to rigid bodies. For the bar to be in equilibrium, the net force acting on it must be zero. This means the sum of the forces in the x direction must be zero. Additionally, the sum of the forces in the y direction must be zero. Nonetheless, although necessary, these conditions are not sufficient for equilibrium to be maintained. We need to satisfy a third condition as well. To see why this is the case, imagine two horizontal forces acting in opposite directions on the bar. Clearly, the net force in the x direction is zero. Since there is no force acting in the y direction, the second equation is also satisfied. However, that is not sufficient to keep the bar in a state of equilibrium. Why, do you ask? Without any additional forces present, the bar is going to rotate, like this. Why does this rotation take place? Because we have a force that is acting at a distance from the particles in the bar. For example, take the center point of the bar. This force acts at a distance from the center particle, thereby giving the rigid body a tendency to rotate. Although this motion may intuitively be obvious, we want to be able to explain it in mathematical terms. Let's show the line of action of the force. Visualize a straight line connecting the line of action of the force to point C. Obviously, we can draw an infinite number of such lines. Nevertheless, we are interested in the shortest line, the line that is perpendicular to the line of action of the force. Let's refer to the length of this line as r. View r as the radius of a circle centered at point C. Now, place a particle at the intersection of the two lines. This force wants to move the particle. But given that the particle is a part of the rigid body, it cannot move independent of the other particles in the body. More specifically, it can only move as long as its distance from point C does not change. This means it has to move along the circumference of the circle. Further, since we are dealing with a solid object, all the other particles need to move in the same manner, which means the bar is going to rotate around point C, like this. Thus, we could say that this force has a tendency to cause rotation around point C. We refer to this tendency as a moment. Putting it differently, we say force P produces a moment about point C. We define the magnitude of this moment as the product of P and R. That is, M equals P times R. Please keep in mind that this equation assumes R is perpendicular to the line of action of the force. The moment has a direction. In this case, since P causes the particle to rotate counterclockwise around C, we say the moment has a counterclockwise direction. Needless to say, this bottom force also causes a counterclockwise moment around point C. Therefore, the total moment at C is 2pr. For the rigid body not to rotate, for it to remain in the state of static equilibrium, the net moment about point C, or about any other point in the two-dimensional space, must be zero. Thus, our third equilibrium equation can be written as. We can use these equations in two ways. They can be used to determine if a given set of forces place the rigid body in a state of equilibrium. Or we can use them to determine the magnitude or direction of one or more unknown forces needed to maintain equilibrium. Let's examine each case using an example. Consider this L-shaped bracket. It is subjected to 4 forces. Is it in a state of equilibrium? Are the conditions of equilibrium satisfied? To answer the question, we have to check all 3 equilibrium equations. The sum of the forces in the x direction is 0. The sum of the forces in the y direction is also 0. Now let's check the moment equation. To do so, we need to pick a point and calculate the sum of the moments about that point. It does not need to be a specific point. It could be any point in our 2-dimensional space. We can pick A, B, C, or any other point on or off the bracket. For example, we could pick this point if we wanted to. Here, I am going to pick point B. Of the 4 forces acting on the bracket, 2 of them are acting directly at point B. So the distance from point B to the line of action of these forces is 0. This means that their moment about point B is 0. The other 2 forces cause a moment about B since there is a non-zero distance between their line of action and point B. Here is the line of action of the 2 Newton force. Draw a line from point B to that line intersecting it at a 90-degree angle. Here it is. The length of this line is 3 meters. Therefore, the moment that the 2 Newton force produces about B is 2 newtons times 3 meters, or 6 Newton meters. This is a counterclockwise moment. The 3 Newton force has this line of action. The distance between point B and the line is 2 meters. Thus, the moment of the force about point B is 3 newtons times 2 meters, or 6 Newton meters. This moment is acting in the clockwise direction. Thus, we have 2 non-zero moments about point B. One is acting in the clockwise direction, and another is acting in the opposite direction. If we assume the clockwise rotation is positive, then we can write the third equilibrium equation as follows. Since the sum is also 0, we conclude that all 3 equilibrium equations are satisfied. Hence, the bracket is in a state of equilibrium. Now, consider this bar. It is subjected to 5 forces, 3 of which have unknown magnitudes. What should their magnitude be in order for the rigid body to remain in equilibrium? Let's write the equilibrium equations. It is good practice to use a sign convention for writing these equations. I am going to pick this convention. X is positive to the right, Y is positive upward, and moment is positive in the clockwise direction. Keep in mind that this convention is entirely arbitrary. For example, I could have picked the counterclockwise rotation as positive if I wanted to. With this in mind, let's write the equilibrium equations. There are 2 forces in the x direction, one acting in the positive direction, and another is acting in the negative direction. So I can write, we have 3 forces in the y direction. 1 is pointing upward and 2 are pointing downward. So we have. Furthermore, to write the moment equation, I need to pick a point. Let's pick A. There are 2 forces that cause a non-zero moment about A. The downward force of 26 newtons and the downward force of By. The distance from the 26 Newton force to point A is 4 meters, and the distance from By to point A is 8 meters. By the way, we often refer to these distances as the moment arm. Therefore, this force has a moment arm of 4 meters, and this one has a moment arm of 8 meters. Both forces create a clockwise rotation around point A, so I can write the equilibrium equation like this. Solving these equations for the unknowns, we get here, the negative magnitude for By tells us that static equilibrium can be maintained only if the force is acting in the opposite direction. Therefore, we can show the forces that ensure the static equilibrium of the rigid body this way. We will continue our discussion on rigid body equilibrium in the next lecture. In the meantime, see if you can solve the following problems.